So this time, this is a story mode. I'm Błażej Kosmowski. I work for Selleo for 11 years, and I'm a lead developer of Ruby on Rails applications. So today's topic is related to a usage of genetic algorithms. So I remember during my school days, when we were learning genetic algorithms, I thought, okay, this is some stuff that I will never use. And imagine my surprise after, many years that I did actually use them. And here is the story about it. So first I owe you some situation report. As you know, I'm working on some project that's related to aggregating data from external services. And this data is related to short-term rentals, properties that you can rent for a short period of time for your vacation or something. So our goal was to scrape those external services or sites for those properties, and the additional requirement here was that we should scrape them only for a given market. And this market was defined by a polygon, just irregular shape that defines, for example, a city or a region or something. And the problem was that the service that we did use did not accept the polygon as area that it should return information for, but it did require a pair of latitude and longitude that did describe the bounding box of an area that you would like to get information for. So what we did need was actually an algorithm that will translate this polygon into one or many bounding boxes that then we'll be able to supply to the API and retrieve the information. But the thing that we did not know was how the API works. So will it return the same amount of properties regardless of the zoom level or maybe of how big the box is? Well, we did not know that. So here's the challenge. And here I would like to show you how it basically works. So let's imagine that this triangle is an area, and to get information for it, we just need to use some bounding boxes represented by those two rectangles that will then send to an API and so on and so on. So as you can see, when we query an API, there is like 1, 2, 3, there are like 7 properties on the screen. So those red ones, we are not interested in because they lie outside of the shape of the market. We are interested in those green ones. However, there's one special case here, that this one is actually shared between two boxes. So it will be returned twice. So our ideal situation, or what we actually are interested in, are the unique rental properties that lie within the shape of the market. And there are some statistics related to it to the top of the screen. So the question is, why not use a single rectangle? It's a polygon, let's just wrap it in a single rectangle and yeah, let's go on. The problem is that the zoom level that we questioned on the first slide actually does affect the set of results. For instance, let's imagine that we have asked our API for the region of United States. And that would be really unusable set of results because it would return hundreds of thousands of results, and that's not good. So they somehow limit the amount of results. And the second issue here is that we get those properties that we are not interested in. They lie outside of the market. So if the market was square, we wouldn't care. But if the market is irregular, we may return more or less properties that we actually do not care. So and the fact is that we already have an algorithm for that. It was not like a tabula rasa for us. It was, we had something, but actually we didn't know how it works. There was a script, we could have analyzed it, but maybe a visual representation will tell you some more. So Anaheim is a region in the United States, or actually a city, and you could see it, but it's covered with bounding boxes. If you look closely, there is a fraction of it here, but it's completely covered with the bounding boxes generated by an algorithm. As you can see, those bounding boxes differ on zoom level, and they cover the same area multiple times. So, as you might suppose, we will get a lot of duplicates, because all this dark area in the middle will be scraped many times. And what is else, when it comes to the dimensions of this market, it's around a couple of kilometers. So our our assumption is that probably you will be able to get the same results with fewer bounding boxes. Less requests, always better. This is a different example. This is a Cape Cod, which is a bit irregular market. It's identified by this blue line in the background. And here there is a different problem, but we'll get to the problems a bit later. So again, why isn't it good enough? It lacks coverage, right? So those extreme cases of top right-hand corner part and bottom left-hand corner part are not covered at all by bounding boxes, so we'll not get results for it. And that's bad. And it also covers a lot of area outside of the actual market boundaries. There's a lot of ocean covered here and here. So if it was not an ocean, we'll get many of unusable or not needed results. Anaheim, as I said, it's again 45 boxes. It's always 45 boxes. Probably it's not, we don't need that many. Lots of duplicates. And those two things and the other things are actually very important because the API is slow and probably it counters scraping. So sometimes it fails. It just tries to make your life hard. Okay, so our theory is that we should just get the bounding box and subdivide it. And then on base of that, we should get some better results. So we did write that, we even test-driven that, and it was really a challenge, but we did it, and this is the result. So it's an Anaheim, it's the same market that we have seen, but now covered with bounding boxes generated by our subdivision algorithm that we called it. So the thing is that, okay, it's cool, but those screens differ, okay? And which one is the most effective? Which setting that generates a set of bounding boxes will be the most effective, will get us the biggest number of properties, but with a the fewest amount of bounding boxes. So we need to identify goals. Our primary goal is that we cannot return less properties than the original algorithm because our customer won't be happy because he wants to scrape as much as possible. And there's a secondary goal, which I have already mentioned, that if we are optimizing something, we'll probably achieve some better settings and less requests, so we should probably use the smallest amount of boxes possible to get the same results. And those are the settings that control the algorithm. Not many of them. The maximum aspect ratio is not very important, it just controls when we subdivide into 4 and when we subdivide into 2. Because if it is a flat rectangle, it's worthless to subdivide it into 4 pieces, but let's just cut it in half, and that's better. Maximum side length and minimum side length. Maximum side length obviously controls the situation when we would like to, for example, cover whole United States. That's bad. Probably we should be much more scoped. And the minimum side length actually is a bit related to the last one, which is minimum coverage. For instance, if our bounding box covers a part of a polygon that reflects an area, and it covers less than 50% of it, then we want to subdivide because we would like to get rid of those blank places. But if we do not control it by the minimum side length, we can get a situation in which there will be a magnitude of really small boxes like 1 meter by 1 meter because we are trying to optimize it as much as possible. So we need some threshold here. That's why we have this minimum side length. Okay, so now we just need to know what set of settings is the best for our situation. And there is this amount of possibilities, so there's quite many. And the API is slow and it counters scraping, so it doesn't make our life easy in finding out. So how can we find this perfect set? We can trial and error it, just try it out, see how it works, maybe write down some results, that's great. But it will take a lot of time and it involves our effort. We can brute force it, so just get some minimum amount and maximum amount and just all combinations possible, and this will take years. And probably it won't be as successful as trial and error approach. And there was this moment when I was showcasing this solution to a friend of mine, Łukasz, and he just mentioned, oh, genetic algorithms, that would be cool here. And I was like, what? That actually makes sense. So genetic algorithms is something that will bring a solution to a problem that's pretty the best solution. Maybe it's not the best one, but it's the most optimal one that we are able to sort out in a limited amount of time. And it's defined by three major things. One is organisms. It's something that evolves, and we need to get it better and better. And this organism is defined by a set of genes. And in our case, those are those settings that we are looking for. And to know if it's better or worse than the previous generation, we calculate something called fitness. And this fitness are those statistics that we have seen on one of the first slides. So in our particular situation, our organism is the subdivision bounding boxes generator, which is the original class name for this thing. And the genes are minimum coverage, minimum side length, and maximum side length. The first one, this aspect ratio controlling one, is not that important in our case. And the fitness will be measured by unique properties within market polygon, those green stars that we have seen. We could have calculated it based on a couple of other metrics, but this is the most important one. We don't want it to be less than the original one, so we have decided that we'll use just this one. So now there was a short research related to what library we should use. There are two major libraries with a good amount of stars on them, which is Darwinic and GGA4R. But the first one has actually more stars, so that's why we have picked that one. Okay, so now some confusion. So this is the core of the thing. So we've got a population of our organism. We decided that the population size should be 10. I don't know why, just a wild guess. And our goal was to maximize the fitness. The more properties we get, the better. So we should go that way. The fitness goal was 700. We know that there is less. So we have just set it to an unrealistic one. So we keep pushing it. And just limited the amount of iterations by this generations limit. And there is some evolution configuration here related to the reproduction and mutation aspects of it. Because how organisms do evolve, they reproduce, so they yes. So what happens is the recombination of genes. So one gene is swapped with another one, right? Or affects it in some way. But there's also a mutation. So it's a random change in one of the gene that just boosts the change. That's why we are here, because of mutations most likely. So, and then we hit evolve and waited a few hours. And there are a couple of results here. The most important for us is this unique valid thing. And the first line represents the original algorithm. So what we can see is that we did not meet our goal. We found actually less parental properties for the same polygon than the original algorithm. But when it comes to this other columns, like how many duplicates we did generate, it's like 3 here. And we did get this result using 8 bounding boxes instead of 45. And 3 duplicates instead of over 3,000, that's great increase. But still, if we tell to our customer, hey, it's so good, but we have scraped less, oh, no, 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 no. So you might have noticed that besides those 3 first settings that we did use for our genes, there is another one, inflation percentage. So we have identified that. Maybe I will show it on some different slides. This is one of the first results. So the blue markers represent those parental properties that were matched from both algorithms. The red ones were those parental properties that were identified by the default one, but not by ours. So this is something that we care about. And there are no green ones that should indicate opposite. So what we first seen, that there is a problem near boundaries and where there is a high density. So those boundaries, we thought, okay, so let's just inflate those bounding boxes just a bit, and then we'll get those rental properties. And that's what happened. So as you can see, we now just do not have that many near the borders, but there is a problem where there is a high density. So at this point, we have decided that, okay, inflation just doesn't work here. We just need to provide a variable zoom. So we have to have many bounding boxes for high density areas that will do that. But we cannot do that. We just don't know if the density is high because we pre-generated this set of bounding boxes before we send it to the scraping hub. Okay, and this is actually a pretty interesting situation because we did the same thing for a different market. And as you can see, there's a really cool thing, because we have scraped a lot of rental properties more than the original algorithm on those places that were not covered by the original algorithm. So it is really cool. We still do miss some in the central region with a high density of properties, but still, it's over 200 rental properties more than the original one. So this time, customer would be happy. And after a couple of optimizations, we get this result. So there's just one that we did miss, and a lot that we get more. But this is the, the set of bounding boxes that was actually suggested by a genetic algorithm that should cover as most. So there are a lot of those. There are like 300, and the original algorithm did use only 45. So there is a room for optimization here, right? So the primary goal was actually met, because in some conditions we returned much more, even though, I mean, we should actually compare the shapes of the brackets to see if this is something that we should go after or not. But yeah, we kind of did achieve it. But using the smallest amount of boxes possible, well, we didn't achieve this goal. So there are a couple of conclusions. So our basic subdivision algorithm does not return as many rental properties as the original one. But when variable zoom level is introduced, we can even scrape more. However, we use more bounding boxes in this case. So the most problematic area for us is the one with high density of rental properties. Over there, we suck with our algorithm. Well, and the last remark is that evolutionary approach can be a problem when the thing that we measure is slow, and the API is slow. So we cannot just generate as many populations, as many generations, as many tests, iterations of this algorithm that would result in, I mean, the best possible solution. So it was okay in our case, and it proved us wrong, but with different algorithm it would be better, because it would be faster. And the ultimate conclusion is that for our particular problem, we should use subdivision-based algorithm with dynamic variable zoom segments. Okay, this we just invented, but this is what should happen. Where the density is low, we can measure it, but when we actually scrape it, then we should stick to the subdivision algorithm. But when we get to the area in which the density of rental properties is high, we should dynamically add more and more rental bounding boxes with different zoom levels that should effectively cover our case in a better way. Yes. So do you have any questions related to this story? Yes, Tomek.
Did you try to tweak the mutation in your several values?
Yeah, many times. I mean, after a couple of iterations or hundreds of iterations, you did notice that it's not getting better. It is just stuck in some way. So it might mean that we just went into local maximum and we just cannot get out of it because the mutation is not good, not big enough to just throw us to a different way of calculating it. But most likely we're just at the limits of our algorithm. It was not good enough without introducing this variable zoom, and that's probably the reason. Yes, David?
How would you like to prevent the case when the guys who you scraped change the zoom where the density of the properties on the specific zoom level? Because then well, as we can see, when we just make a lot of zoom levels at a given area, it usually covers. When it comes to anti-scraping, we did use countermeasures to that. I don't want to mention what, because they will, but I can tell it after. So they probably didn't know. Yeah. Any other questions? That's great. Okay, so I think there is a kudos for a section here. So Marek Caputa was an author of the statistics script that did allow us to just throw a set of bounding boxes in it, and then it will result. It will return us a result in form of all those statistics that we are interested in. And Łukasz Pawlik obviously already mentioned those genetic algorithms, and yeah, that's where the story started. And obviously, if you look closely, there is some guy here, and he was coding this whole thing during Christmas. So
if you have some spare kudos, you can send them to him. I don't know, I cannot see. Thank you.